I'm just gonna get started. So, your first homework assignment will be due next week on Thursday, the 4th. That is the Introduction to Mastering Physics and the Physics Primer. They're both like intro assignments. They should be pretty straightforward. And then the first homework assignment that's actual homework is going to be due on Wednesday, the 10th. But I gave you until the Thursday of that week because, because it had all the days from last year and they were all Thursday. They were all off by a day because I just translated. But I gave you until Thursday for that first assignment because you might have a little trouble getting the homework working. In general, to get access to Pearson, to get the homework working, you'll need a code. You can find the code by going to, I think it would be eCampus. So there's probably a link from the Wave portal. It's called the bookstore or eCampus. Or I think you can go to ecampus.ccsj.edu, but I'm not 100% sure there. Because my access to this is completely different and I never see what you guys see. And then that'll give you the access. And on eCampus, there will be a link to something with VitalSource, which will give you the access code. I don't think you can get it directly by going into the publisher content section on Blackboard. I think you actually have to go to eCampus to get it. If you're still having trouble with that, I'm willing to sit down with anybody to walk through it. I'll be around on Mondays and Wednesdays, or I could do it after class for anyone who wants to go through it after class today. Because we will not be having a lab today. We'll do our first lab next week on Wednesday. In general, the labs will not take the whole scheduled time, and you guys will be able to leave as soon as you're done. Because you don't want to be stuck here until the end of the scheduled time, and I don't want to be stuck here until the end of the scheduled time. Any questions about that? Okay, let's get started with chapter 2 on motion. So we're going to start with what is one-dimensional kinematics. So kinematics is describing motion, not talking about what causes it, but how it happens. And we're going to do one-dimensional kinematics, just dealing with one dimension of motion. So here, for example, we have a particle that moves over time. It moves in the positive x direction for 2 seconds, then it turns around and starts moving in the negative x direction. And we'll learn how to describe that kind of motion. We'll actually be able to solve some problems because, for example, it turns out a falling object has the property of constant acceleration, so you can solve problems with constant acceleration. So to start out, we'll talk about position, distance, and displacement and what these are. We'll talk about average speed and velocity and the difference between them. Speed is a scalar quantity, velocity is a vector quantity. We'll talk about instantaneous velocity. We'll talk about acceleration. And then we'll talk about motion with constant acceleration, the most common of which is falling objects, and how to apply the equations of motion. And lastly, we'll discuss freely falling objects, which is the most common case of motion with constant acceleration you're going to run into. I mean, most of motion with constant acceleration isn't uncommon, but like the most common problem for constant acceleration is a falling object. And for freely falling object, that acceleration is just, it's the same for everything. So it's sort of a common special case. So if you want to talk about motion, you first need to be able to talk about where stuff is. because motion is about stuff changing where it is. So you first need to be able to talk about where stuff is. So you need to set up a coordinate system. You need to define some zero location, some starting point, and a positive direction. Here, for example, we have the origin at x equals 0. Positive here is towards the right. And so as this is the initial position, xi, which is some distance from the origin. And this is the final position, xf, which is some different distance from the origin. And we can describe these positions by, how many meters they are from the origin. We're just dealing with one dimension. So we're not dealing with any other direction, only one direction of motion. Well, back and forth, but one dimension of motion. Let me quick. Oops, no. So now, once you have a position, we talked about what a position is. It's how far you are from your reference point, the origin. You can talk about distance. Distance is the actual distance you travel. How far you travel. If I go 1, 2, 3, 4 meters this way, and then another 4 meters back, my distance is 8 meters. I've traveled 8 meters. So distance is the total length of travel. If you drive from your house to the grocery store and then back, 4.3 miles there and 4.3 miles back, you've covered a distance of 8.6 miles. That's distance. Displacement is change in position. If I go from my house to the grocery store, going 4.3 miles in the positive x direction, and then I go from the grocery store to my friend's house, going 4.3 and 2.1 miles in the negative x direction, so that's 6.4 miles in the negative x direction, my displacement will be negative 2.1 miles. So distance is total distance you traveled. Displacement is final position minus initial position. That's displacement. Delta x. That's a common way to write displacement. The displacement is your change in position. So if I go 1, 2, 3, 4 meters this way, and then 1, 2, 3, 4 meters back, the distance I covered was about 8 meters. My displacement is 0, because I'm back where I started. So displacement is the distance from start to finish, while distance is the actual distance you travel. And so they end up different a lot of the time. And displacement will have a sign. Distance will be positive all the time. But displacement, here we're in negative 2.1 meters from our starting position. We went in the negative direction. There's a direction indicated there. When we get additional dimensions, displacement has a size and a direction, while distance doesn't. It's just how far you travel. So if you take a trip from your friend's house to the grocery store and then to your house, so you start at your friend's house, you go to the grocery store, and then you go to your house, what's your displacement for this trip? And what's the distance for this trip? Sorry, can you repeat that? Um, no, it's more than that. Because you go 2.1 miles, 4.3 miles, so that's 6.4, and then back 4.3 miles, which is 10.9 miles. So the distance, if we do the distance, that's going to be 2.1 miles plus 4.3 miles plus 4.3 miles, which is 10.7 miles. And the displacement is final position minus initial position. So that's delta x will be 2.1 miles minus 0 miles, which is 2.1 miles. And it's positive. Everybody got that? Here we have a ball that travels from position minus 5 meters to a position positive 6 meters, and then back to position positive 3 meters. So what will be the displacement of this trip? And what is the distance traveled in this trip? So I'll give you a little bit of time to work this out. So you have a ball that travels from negative 5 meters to 6 meters and then back to 3 meters. Displacement, delta x, will just be final position minus initial position. So that's going to be the final position, 3.0 meters minus negative 5.0 meters, which will be 8.0 meters. And the distance will be, we go from negative 5 to 6, so that's 6.0 meters minus negative 5.0 meters, throw an absolute value on that, plus from 6 to 3, so 6.0 meters minus 3 meters. This is 11 meters plus 3 meters. So you get something like 14.0 meters. Is the distance. As you go from -5 to 6, that's 11 meters. 5 plus 6. And then from 6 to 3 is another 3 meters. Good. So now that we know what distance and displacement are, we can talk about average speed and average velocity. So average speed is distance over time. The average speed here, where we had, it goes for 4 miles at 30 miles per hour, and then 4 miles at 50 miles per hour. Would you expect the average speed to be 40 miles per hour, more than 40 miles per hour, or less than 40 miles per hour? Remember, it's total distance over time. It actually works out to be less because it spends more time at 30 miles per hour than it does at 50. So this has a bigger effect on the average speed. Now, average velocity is displacement over time. So average velocity, which is written in V bar, is displacement over time. Or final position minus initial position over time. So because average velocity is displacement over time, if I walk here and back, my average speed was, I don't know, maybe a meter per second. But my average velocity is 0 because I came back to where I started. So my total displacement is 0. So for example, the average velocity of an Indy 500 race is 0 meters per second because it starts and ends at the same place, or it should. So the displacement is quite small because you're going around in a circle. Now, you can also graph position versus time, and there's a graphical interpretation of average velocity. So the average velocity, if we plot it position versus time, the average velocity from 0 to 4 seconds will be the slope of this line that passes through the line at 0 and 4 seconds. The slope of that line is the average velocity. If you make the time period smaller and smaller, eventually you'll get the slope of the tangent line. That is the instantaneous velocity. So from a calculus point of view, the instantaneous velocity is the derivative. So here we have a dog travels 2.3 meters in 4.5 seconds. What is its average speed? I'll give you a minute or two to work this out. Okay. Speed is distance over time. So that's 2.3 meters over 4.5 seconds, which will give us 0.51 meters per second. It actually gives you 0.51 repeating. Just round it off. Here we have a walker that travels 400 meters north in 450 seconds, and then 250 meters south in 350 seconds. So what is the walker's average speed and what is the walker's average velocity? This is a bit tricky. So this is going to be the time you're going to divide by for this is the total time. So let's start with speed. That's going to be total distance over total time. So our total distance is 400 meters plus 250 meters. And our total time is 450 seconds plus 350 seconds. That gives us 650 meters over 800 seconds, which comes out to 0.8125 meters per second. We treated all those distances as positive. But our first distance is north and our second distance is south. So for displacement, for the average velocity, we start with plus 400 meters minus 250 meters, because north is positive in this case and south is negative. I'm treating north as positive. And then the time is the same, 450 seconds plus 350 seconds. And so that gives us 150 meters over 800 seconds, which comes out to 0.1875 meters per second. So the time is the same, but the distance is 650 meters, while the displacement is 150 meters. Yeah, everybody got that? Now, instantaneous velocity is basically the limit. So the definition of instantaneous velocity, it's the limit as you do the same thing you do for average velocity, except you make the time period smaller and smaller and smaller and smaller. It is the limit as delta x, as delta t goes to 0 of delta x over delta t. So velocity is, limit as delta t goes to 0 of delta x over delta t, or in actual calculus terms, that is dx dt. It's the derivative in terms of time. And that's just the slope of the curve. It's the instantaneous rate of change. So we evaluate the average velocity over shorter and shorter periods of time. As time becomes infinitesimally small, we get the instantaneous velocity. In everyday life, there are tools to measure instantaneous velocity, like speedometers, but this is just, this is a calculus definition without resorting to just saying derivative. I don't know where you guys are in math, but if you've done calculus, it's just a derivative. So here we can see the average velocity being measured over shorter and shorter intervals, and eventually you get the slope of the tangent. It's just the slope of the line at that point. And that would be the instantaneous velocity. So here, The slope between 2 points on the curve is the average velocity, while the slope of the curve, of the line tangent to the curve at the point in question, is the instantaneous velocity. So here is the instantaneous velocity at 0.5 seconds, up about here, greater than or less than the same as the instantaneous velocity at 1 second, about there. Which one has the larger velocity? At 0.5 seconds or 1 second? You're saying 1 second? Anyone else? Well, the steeper the slope, the bigger the velocity. So at 1 second, it's further along, it has a larger position, but the slope is less steep. So here, where the slope is steeper, at 0.5 seconds, has a higher velocity. Now, we talk about velocity. Velocity is the rate of change of position. Acceleration is the rate of change of velocity. And if you want, I can keep going. The rate of change of acceleration is jerk. The rate of change of jerk is either jolt or snap. And then if you choose snap, then the rate of change of snap is crackle, and the rate of change of crackle is pop. Because no one uses those terms, so people decide to be funny. But yes, the rate of change of velocity is acceleration. So average acceleration, let me do average because that's what this book is doing. Average acceleration is change in velocity over change in time. So that's final velocity minus initial velocity over final time minus initial time. Instantaneous acceleration is just the derivative of velocity. So dv dt. So some typical accelerations. The units for velocity were meters per second, because it's how many meters you travel in a second. The units for acceleration are meters per second, because we're looking at the rate of change of velocity. So that's meters per second squared. So typical accelerations, an ultracentrifuge has a acceleration of something like 3 × 10⁶ meters per second squared. A bullet fired from a rifle is 4.4 × 10⁵ meters per second squared. A batted baseball is 3 × 10⁴. A click people writing itself is around 400. The acceleration required to deploy airbags in your car is around 60. That's about 6 times the acceleration of gravity. The acceleration of a bungee jump is about 30 at the end when you're bouncing back. The acceleration of a high jump is around 15. The acceleration of gravity for a dropped object is 9.8. 9.81 is what the book is using, but it does vary with latitude. So 9.8. The further north you go, the bigger the acceleration of the gravity is. Has to do with the spinning of the Earth. An emergency stop in a car is about 8 meters per second squared. An airplane during takeoff is about 5 meters per second squared. An elevator is around 3 meters per second squared. And the acceleration of gravity on the moon is around 1.62 meters per second squared. So those are some accelerations. And here's a graphical interpretation of average and instantaneous acceleration. Here we have a plot of velocity versus time. So average acceleration is change in velocity over change in time. So it will be the slope of a line connecting 2 points on the velocity versus time graph. And instantaneous acceleration is the slope of the tangent line. So that's the derivative at that point of velocity versus time. So notice that in the previous thing where we were looking at velocities, this was position versus time. This is velocity versus time. Now, acceleration is the general term. If you have changing velocity, it's an acceleration. When we talk about deceleration, that is slowing down. Slowing down doesn't necessarily mean an acceleration in the negative direction. It means an acceleration in the direction opposite to the velocity. So if acceleration and velocity are in the same direction, if they're both positive, your speed will increase. If your velocity is positive, but your acceleration is negative, your speed will decrease. If your velocity is negative, but your acceleration is positive, your speed will decrease. So these two, where acceleration and velocity point in opposite directions, those are deceleration, decreasing speed. And here, speed is increasing because velocity and acceleration are both negative. So the car will be speeding up. So, these two have positive acceleration, these two have negative acceleration. These two have positive velocity, these two have negative velocity. So if you have a car that can go from 0 to 100 kilometers per hour in 8 seconds, what's the average acceleration of the car in meters per second squared? So I will give you a helpful tool. So you could do the conversion here. So one of the common conversions you'll have to do is from kilometers per hour to meters per second, because we talk about things like cars in kilometers per hour a lot. So the conversion for kilometers per hour to meters per second, well, we have one. It's actually easier to do it the other way. I'll do it the other way. You have 1 meter per second, and you want to go to kilometers per hour. Well, you have 1,000 meters in 1 kilometer, and you have 3,600 seconds in 1 hour. So 1 meter per second equals 3,600 divided by 1,000, or 3.6 kilometers per hour. So a very useful conversion factor is 1 meter per second equals 3.6 kilometers per hour. And that is exact. So you don't have to worry about significant figures for it. So you have a car that can go from 0 to 100 kilometers per hour in 8.6 seconds. I'm sorry, in 8.0 seconds. What's the average acceleration of the car in meters per second squared? The average acceleration is final velocity minus initial velocity over, well, in this case, it'll just be delta t. So first step, let's convert 100 kilometers per hour to meters per second. So that'll be 1 meter per second is 3.6 kilometers per hour. So that will come out to 27.7778 meters per second. I'll round it to 47.7 repeat. Now we're trying to find the average acceleration. So that's final velocity minus initial velocity over change in time. This 100 kilometers, that's our final velocity. Our initial velocity, that's 0. That's what we started at. So final velocity, 27.778 meters per second minus 0 meters per second divided by the time. How much time did this take? Well, it took 8 seconds. So this comes out to 3.4722 meters per second squared, but that's far too accurate for this, so let's round it to it's about 3.5 meters per second. Two significant figures for me. I'm assuming the 100 is 40. Everybody got this? You okay with me erasing it? So here we have a cyclist that's riding in a straight line. They have an initial velocity of 3.5 meters per second and an acceleration of -1 meters per second squared for 2 seconds. Then they coast with 0 acceleration for 3 seconds. And finally, they accelerate at 1.5 meters per second squared for 2 seconds. So the question is, what is their final velocity and their average acceleration? So to find final velocity, the easiest way to do this is we could rewrite our acceleration formula. We know that the acceleration is v final minus v initial over delta t. So acceleration times delta t is v final minus v initial. So v final is v initial plus acceleration times delta t. So we can do that for each segment to find the velocity at the end of each segment. And then we can use the final velocity and the initial velocity and the total time to find the average acceleration over the whole trip. so let's go through the segments. The first segment, we start with a velocity of 3.5 meters per second and an acceleration of -1 meters per second squared for 2 seconds. So, velocity 1 is 3.5 meters per second. Acceleration 1 is -1.0 meters per second squared. T1 is 2.0 seconds. So velocity 2 is going to be velocity 1 plus acceleration 1 times T1. So that is 3.5 meters per second plus -1 meters per second squared times 2.0 seconds, which comes out to 3 minus 2, which is 1.5, 3.5 minus 2, which is 1.5 meters per second. That's velocity 2. That's where we're at the end of the first segment. The end of the second segment, well, we're coasting with 0 acceleration for 3 seconds. So velocity is not going to change. Velocity 3 equals velocity 2. And then for the third segment, velocity 4 is going to be velocity 3 plus acceleration 3 times time 3. Acceleration 3 is 1.5 meters per second squared. Time 3 is here, 2.0 seconds. So velocity 4 will be 1.5 meters per second. This will be 1.5 meters per second plus 1.5 meters per second squared times 2.0 seconds, which velocity 4 will end up equaling 4.5 meters per second. Now, that is our final velocity. Our average acceleration, well, this is our formula for average acceleration. Where do I have some space? I'll put it over here. Acceleration average is, final velocity, 4.5 meters per second, minus initial velocity, 3.5 meters per second, divided by total time. Well, that's 2 seconds plus 3 seconds plus 2 seconds. So this comes out to 1 meter per second divided by 7 seconds, which is 1/7, 0.14 meters per second squared. I'm not going to bother with more decimal places. It's 1/7. Yeah. Any questions about that process? You break it up into the segments, you work out what the speed is going to be at the end of each segment, and then you can calculate the whole acceleration by using final velocity minus initial velocity over total time. Sorry? Oh. Okay. Okay. So everybody got this? We'll erase.
Wait, can I take a picture of you?
Sure. So if acceleration is constant, we get linear changes in velocity. So given constant acceleration, the velocity at any time t is the initial velocity plus acceleration times time. That's a 0 for time 0. So average velocity will end up being the average of this, which is 1/2 initial velocity plus final velocity. And this allows, knowing this, the average velocity lets us figure out our displacement, our total distance traveled. So we can take the average velocity and the position and use that to calculate the position as a function of time. So the position as a function of time is going to be x0 plus 1/2 initial velocity plus final velocity times time. And if we plug in this equation for final velocity there, we get our useful actual formula for position. Position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. So this is how you can get this by using the average velocity and some algebra. It falls out very nicely from calculus. So if you take this and you take the derivative of it twice, you get constant acceleration. Calculus was invented to do constant acceleration problems. Additionally, with some more algebra, you can get velocity as a function of position, completely getting rid of time. So that is that velocity squared is equal to initial velocity squared plus 2 times the acceleration times, this is usually written as delta x. But final position minus initial position. So here is how to find position given velocity, acceleration, and time, initial velocity, acceleration, and time. Here is how to find, final velocity given initial velocity, acceleration, and time. And this relates velocity, position, and acceleration without referencing time. So sometimes you just want to go, directly from, you don't want to deal with time, you're not interested in time. So this saves you the step of having to go through time. And so the relationship between position and time is a parabola. It follows a characteristic curve. That curve is a parabola because it's a quadratic equation. So here are the equations in question. Velocity is, if you're dealing with velocity, time, and acceleration, final velocity is initial velocity plus acceleration times time. Average velocity is 1/2 initial velocity plus final velocity. You can also do position is 1/2. Position is initial position plus 1/2 final velocity plus initial velocity, close parentheses, times time. But more useful and more commonly used will be position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. And then if you just want to use velocity, position, and acceleration and don't want to reference time, final velocity squared is initial velocity squared plus 2 times acceleration times displacement, delta x. Final position minus initial position. Any questions about these equations? These are the one-dimensional equations. We'll come back to use them again when we get to more dimensions. All you do is basically repeat them for each dimension. So you have this for x, and then you do it again for y, replacing all the x's with y's. But that will be in a future chapter. So, if you throw a ball straight up in the air with a velocity of 4.9 meters per second, the acceleration of that ball downwards due to gravity will be minus 9.8 meters per second squared. So we know our initial velocity is 4.9 meters per second, and our acceleration is negative 9.8 meters per second squared. So what is the velocity of the ball after half a second and after 1 second? So these are the relevant equations. Look for the one that'll give you velocity given initial velocity, acceleration, and time. Oh, okay. So the relevant equation here is that velocity is initial velocity plus acceleration times time. So first we have our initial velocity is 4.9 meters per second plus negative 9.8 meters per second squared times our time, 0.5 seconds. After 0.5 seconds, well, 4.9, 9.8 times 0.5 is 4.9. So this comes out to 0 meters per second. You throw a ball upwards at 4.9 meters per second. After half a second, it will come to a stop at the peak of its flight. Then, after 1 second from the initial start, velocity would be again 4.9 meters per second. Our starting value, again, minus 9.8 meters per second squared for acceleration. But now we multiply by 1.0 seconds. So here, this will be traveling 4.9 minus 9.8 is negative 4.9 meters per second. It'll be coming down at the same speed it went up. And if you work out the position, it'll actually be at the same height you threw it at. You can work it out with this equation, actually. So If acceleration is some number and initial velocity equals final velocity, these will cancel. So acceleration times change of position has to equal 0. Acceleration is not 0. So delta x has to be 0. Let's see. So we have a little more time. So that's some review. Yeah, we'll go over one more question and then we'll be done. So here we have a boat leaving a marina. It's traveling at 1.5 meters per second. Yes? We'll come back and do it again. Okay, well, we can leave off. You have questions about this? We can stop here. That's fine. This is where I was roughly planning to stop anyway. So are there any questions about what I just covered? Anything you'd like me to go over in more detail? Yes. My office hours are officially from 10:30 to 11, but I'm usually around all day. I teach from 9:30 to now. 8:30 to now, sorry. Okay,
Yeah, I think you download the app.
oh,
Is there any way to simplify this? You know, cause I feel like
I mean, this is, you can go through it and say,
the plane still.
so these are the equations that are relevant for kinematic stuff, actually really just these three.
So like those are the main equations you use the last problem.
Yeah. So these are the relevant equations. So here, if we look at this problem, we can go through, I'll go through and do this problem again. And I'll do it in a way you can figure out which equation. Yeah. I'm going to go through the process by how you choose them. That's what I'm saying. So, sorry if I'm going a little quick on these then. So here, let's go through what we know and what we're looking for. So what we know, let's go through our givens. So we have a velocity of 4.9 meters per second that the ball is thrown at. So that is, our initial velocity is 4.9 meters per second. I'm listing what I know and what I'm looking for, and then I'll tell you how you use that to find which equation to use. Yes. And then we have an acceleration. This is acceleration of negative 9.8 meters per second. And then we're asked, what is the velocity? So what we're looking for is final velocity. So I'll put a question mark next to it, but I'll write down the variable. And we're given a time. So we know time is 0.5 seconds. So here, these are the variables that we're dealing with. We have initial velocity, final velocity, acceleration, and time. We don't have any positions, so we don't need to think about this equation. So we want the equation that has these variables in it and nothing else, ideally. If you can't find that, you might have to think about ways that you connect equations, but you don't need to do that for this. Or you shouldn't really need to do that much for these problems. At least for this chapter. So here we have velocity v. What we're looking for is initial velocity, our starting velocity, plus acceleration times time. So this will be the equation we use, because it's telling us what velocity is in terms of time and acceleration. So we can write velocity is initial velocity plus acceleration times time. Our initial velocity is 4.9 meters per second. Our acceleration is negative 9.8 meters per second. And our time is 0.5 seconds. So that's, 4.9 meters per second, negative 9.8 times 0.5 gives us negative 4.9 meters per second. And so 4.9 meters per second minus 4.9 meters per second is 0 meters per second. And then for 1 second, we just do it again with 1 second instead of 0.5. So that's, this is V1, this is V2 or something like that. So this would be 4.9 meters per second plus negative 9.8 meters per second times 1.0 seconds. And that will come out to negative 4.9 meters per second.
That makes more sense.
Okay.
Yeah, that makes more sense.
Yeah. Some of this is trying to do things at the time. But yeah, okay. So that's the approach. I'll try and talk through it a little more when doing these. And I think I'll try and go through and write up solutions on the slides so I can talk through them a bit, hopefully, right? But the general idea is you identify what you know, and that lets you pick the appropriate equations. Yeah, so I'll write up on the slides for future lectures. So I'll see you guys next week. I will end the recording.